Hey guys, I'm Benji Braun. I'm going to introduce our next speaker. You start coming to this conference long enough and they put you to work. Um, oop. So our next speaker has a 2-year-old daughter who loves to sing Born to Run and a 5-year-old son who encourages her. Everyone welcome Jared Lander.
All right, cool. So today we're going to talk about maps because geographic data just keeps getting bigger and bigger. And we're going to use new tools today. This is the modern GeoStack. So these are maps. We're going to talk about this again because this is a follow-up talk to my talk, Mapping Large Data. But now we're going to do it with bigger data and new tools. And that talk itself was a follow-up to using R for GIS and mapping. I just keep doing more and more maps. This is my life now. So our goal for today, we had to store a lot of large data in PostGIS/TimeScale. We are going to execute some spatial queries, mainly of DuckDB. We will extract the data from the database into GeoArrow for interactive consumption, and visualize it with deck.gl. So we have to fill in all of these checkboxes. So let's get started on that. And first up, we have to store the data somewhere. It has to go live somewhere. Everything is going to go into Postgres. Everything I do anyway is always going to be a Postgres database, so we're going to put our geodata there. And it's PostGIS that enables us to do geographic operations on the data living in Postgres. And we will use timescale because everything is a time series. I heard that from Jeff Ryan. Everything has a timestamp to it, so you might as well take advantage of that. So luckily, Timescale puts out a Docker image called Timescale HA, and that has GIS built into it. And I added some other Postgres extensions. I added PG curl to make curl requests, DuckDB FDW to work with DuckDB data, Parquet FDW for Parquet data, and H3 for quickly assigning lat long into hexagons around the world. So now that we have our database planned out, let's look at the data. If we do a quick query for our tables, we primarily care about 3 of the tables. The world table, which has national boundaries, airports, which are airports around the world, and locations, which is randomly generated data. If we look at the first few lines of the world table, it's world boundaries. We have the country name and the short version and the geometry. Don't worry about the geometry being stored as binary. That's just the way it's displayed on the presentation. Then we have the airports table, which is airports around the world. I thought I was just pulling airports in Europe, but OpenStreetMap had other thoughts. And then locations is just literally data I made for giving talks about geospatial data. All right, so it's literally just that. But we're not going to use any ordinary tables. We are going to use hypertables. These are a feature of timescale, and it will automatically partition our data, mainly based on time. And this will give us much faster reading and writing to the database. So let's dig into it. You actually first create a normal Postgres table. It is similar to any other Postgres table. Notice we have the geometry column and we put constraints on it like the dimensions, the type, the projection. And I added a spatial index so things compute faster. We then create a unique index. In this case, each ID and timestamp must be unique. And we do that so we can take advantage of hypertables. We are then going to say select create hypertable. This creates a hypertable, which is really a bunch of little tables. There's a bunch of partitioned tables all masquerading as one table. And this happens automatically. It will automatically partition my data into different tables based on time. And then I also added a dimension for the ID, the hash of the ID. So our IDs and our time will be going into different tables. So this way, if you have a where clause, instead of scanning over all of your data, it only needs to scan over certain tables in the database. And it all happens opaquely to you. You don't have to worry about it. It just happens automatically. You search for a certain time, it scans the necessary tables. You search for a certain ID, scans for the necessary tables for that, and brings you back the data. It's really, really awesome for no cost effort to you. So we store the data. It's all in Postgres. We're great. Good to go. So let's continue, and let's try a few different spatial queries. Our goal is going to be to find, of those location data points, which ones are near airports, near being defined as 5 kilometers. So the process is roughly going to be create a 5-kilometer buffer around each airport polygon, compute the intersection between the points and those buffers, and just collect those points in that intersection. Now, the first tool I always reach for is R. I always do everything in R. So in order to get our data, we first need to make a connection to the database like we would for any other Postgres database. And I use environment variables to store my secrets, as good security entails. I then read all the data from the database into memory using SF or readsf. And this assumes your data fits into memory. And it could take some time, usually not that long, but it could take some time. Then the buffering is easy. You simply say stBuffer and give it the distance you want, in this case, 5,000 meters. And this works. Even though our data is in latitude, longitude, it works because SF by default uses S2 math, so it uses spherical geometry, so it does it all for you. Give it meters, it computes it for you. But I will let you know when this finishes. Just on the England and the Netherlands, which are 1,900 rows, it took 45 seconds. And we have, I believe, 23,000 polygons here. So I'm not sitting around waiting for this. So I said, let's try it in PostGIS. Let's see if I can write some SQL code. So I go ahead and write this, and it's fairly easy. You first have to convert your geometry into geography, so you could use spherical math, call stBuffer, then convert it back into geometry. And this works. And all in, that takes about 8 seconds. Not so bad. All right, I'm happy with that. But let's check out DuckDB, because it's all the rage right now. So when you're in DuckDB, you first have to install and load the Postgres extension and the Spatial extension. And it automatically will pull from the internet, but if you're in a lockdown environment, you can give it local files to pull from instead. You then attach your DuckDB instance to Postgres. That's what this attach statement does. So this way, I can directly query Postgres tables. I'm going to create a view in DuckDB just so I don't have to type as much, because there's this command here. I need to convert from a Postgres EWKB column into a DuckDB geometry, and I do that with stgeo from text WKB. I don't want to type that every time, so I make a view just to make it easier to compute, but otherwise I'm reading straight geometry data. Now, unfortunately, DuckDB expects your buffer distance to be in whatever units your projection is. I'm in lat long, it wants degrees, and I'm not doing that. So I'm going to transform my geometry into a meters projection, in this case 3857, which is Web Mercator, which should be meters all across the globe, compute the buffer of stBuffer, then compute it back into lat long. All of that takes about 8 seconds to do, and that includes getting the data from Postgres and converting the Postgres geometry type. But something seemed off about it, so I plotted it. And when I plotted it, you can see the DuckDB buffer in purple is smaller than the SF and PostGIS buffer in yellow. Something felt wrong, and that's because 3857 has distortions. So I needed a better projection. In comes Universal Transverse Mercator. This divides the world into 122 slices, 60 above the equator, 60 below, and both poles. So the idea is that I'll project each polygon into its respective slice of the Universal Transverse Mercator, compute the buffer in each individually, compute it all back into lat long, and that's our answer. So first, I've got to create this UTM table. It was very hard to find the data for that. There's a bunch of different shapefiles and GeoJSONs I had to combine. But luckily, DuckDB can read geospatial data simply by calling stread. You say stread, give it a file, and it becomes a table in DuckDB like that. Pretty awesome. I then do a spatial join to join in our polygons into the different projection areas for UTM. I convert each polygon into its own projection, then call stBuffer 5000, convert back to lat long, and everything gets combined back together. All in, this was 7 seconds. This is really fast. That includes moving the data out of Postgres, doing the spatial joins, the buffering, the reprojections, converting it to text in this case so you can read it better. And notice here there's an argument always xy. That's because the open standard for 4326, it should be longitude, latitude. Did I get that wrong? No, it should be latitude, longitude. All the commercial software does latitude, longitude, but all the open source software does longitude, latitude. And you have to remember that. And DuckDB will do whatever order it comes in. So I needed to tell it Yes, the open source software is violating the open standards, so do longitude first, then do latitude. But that's not too hard. So now we look at it, and DuckDB finally agrees with SF. If you were to zoom in, you would see the SF buffer is a little jagged. That's because what S2 geometry actually does, it creates a bunch of little segments it combines together. So I would much rather go with the PostGIS or go with DuckDB. And just because I wanted R to do a good job, I use the Geos library, which is a Rust library that is a really fast geometry calculator. And I reenacted the whole splitting up the data, projecting into different projections, computing the buffer, combining back to lat long. And all in, that was about 12 seconds. I could have done that in parallel. I could have tweaked things, but I was happy enough with 12 seconds versus 7. So then something about the airport seemed odd to me. And doing a simple count, I noticed there were duplicated airports. Some were 7 times, 6 times, some with NA, some which had no name at all. So I looked at an example. Stapleford Aerodrome is listed in both England and the Netherlands with the same exact polygon and the same exact name. So which is correct? To find out, I did a spatial join between the airports and the world boundaries to see which country it seemed like it was in. And then if the name of the country listed by the airport was the same as the name of the country listed as the map, they were the same. And I had to make a special case for the United Kingdom because the United Kingdom is just 4 countries in a trench code, right? So I needed to combine them all together here, but otherwise this works. And we see I started with 23,000 rows and I ended up with 3,000 rows. There was far fewer than I thought. And it turns out they really were all in Europe like I asked for. It was just completely mislabeled and duplicated. So now that we have our good airports, we know how to make buffers, let's actually find which locations were in those buffers. So it's pretty simple. This is in PostGIS. You compute the buffer on the fly. I could have pre-computed it, but I computed it on the fly. I then did a spatial join of points and buffers and got my points that were in those buffers. And I'm comparing 300,000 points against 3,000 polygons, and it took 7 seconds. This is largely thanks to the spatial index, otherwise it would have taken 2 minutes. I could have sped it up more by using H3 hexagons, but that's for another talk. But let's see how DuckDB did. First, I'm going to create those tables locally. Instead of using the view from Postgres, I'm going to bring it locally to DuckDB. This way I could take advantage of DuckDB's spatial indexes, which you see here at the bottom. And I pre-joined in the CRS numbers. So then I created the buffers, which includes doing the conversion to the individual projections, computing the buffer, projecting back to lat long, then doing the spatial join of the 300,000 points against the 3,000 polygons. This took less than 1 second. So we can compute 23,000 buffers in less than 7 seconds, and we can do the spatial join of 300,000 points against 3,000 polygons in less than a second. This is blazing fast for geospatial data. It's amazing what DuckDB can do. So now it's time that we've executed all of our spatial queries, we're happy with them. Let's pull the results into Arrow data, because Arrow is going to let us do some really great stuff. Using DuckDB and Postgres, we could just simply say copy from the Postgres table to Arrow using the GDAL format. This should work. But the Arrow driver is missing from the GDAL that ships with DuckDB. So I'm filing an issue with GitHub because I asked on Twitter and they said file an issue, and we'll do that. So instead, we have to turn to R. And we're going to use the Arrow database driver, so it's ADBC instead of ODBC. We're going to read the table, but not into R memory. We are actually going to stream it into R, then into Arrow without everything ever coming into R memory in total. Now, the problem is Postgres geometry types are different than Arrow geometry types. So I have to write a little function here, fix batch, which thanks to Dewey Dunnington, I think Dunnington Dewey, thanks to Dewey, helped me figure this out. And you have to convert the geometry into a GeoArrow vector. And this function will be applied to each batch of the data. So we'll read a little bit from the database, fix it, dump it to Arrow, read, dump to Arrow. So it's going to stream from the database into Arrow. So if I have 1 billion rows, it never all comes into R memory. It just streams through R into Arrow. It's really amazing how great this is. And this, on about 300,000 rows, took about half a second to go from Postgres to an Arrow file, including fixing the geo column. Doing the same thing with the airports data. In this case, I have 3 different geometry columns. I will fix each one of them within each batch and stream it all into an Arrow file. It's really that simple thanks to Arrow. Not as nice as that one SQL statement, but this is great. Blazing fast, simple to write. So we have all of our data in Arrow, which we can now use to make those maps. We can go ahead and finally put it on the screen. Now this is going to involve a little bit of HTML and a lot of JavaScript. So first, you need to load up all of the JavaScript libraries. And if you don't have access to the internet, you could use local copies. We are loading up deck.gl for mapping, along with deck.gl layers, which integrates Arrow. We are using Leaflet and deck.gl Leaflet to combine the two. We'll use the Arrow library. We could use Arquero for manipulating the data. I'm not going to go over all of them. Then the entirety of the rest of the HTML could just be this: a div to hold the map, and then call the JavaScript code, which is in a module because it has async data loading. Now, I don't really write great JavaScript code. I learned how to write it by copying websites in the 90s, and I stayed just about there. So first up, we need this GeoArrow deck.gl library, which doesn't load properly. So we need to pull it from the document window. And we've made great strides thanks to Joe Marlowe on my team, making pull requests and fixing up this JavaScript library. We've done a lot of great effort for this. We then load up our data. This is Arrow data, which is hosted on a web server, and we are going to asynchronously load it into JavaScript. We then create a leaflet object that will have our map, and we will center it at a certain point. Now, I'm combining Leaflet with deck because I wanted that look and feel of Leaflet. One day I'll go purely deck, but for now I'm combining the two. We then have to create an overlay group, which is going to hold all of our data layers. It will hold our points, it will hold our polygons, and anything else we want. And it will be empty for now. We then get layers for OpenStreetMaps and for imagery data, the top-down satellite view. And we're going to add the street maps to the map right now, and we'll add the imagery later when users want it. I then have to create a panel to hold my controls, the toggle between street maps and imagery, and to control which data layers you want. That's really all this is doing. There's an object there to hold the background tiles, and there's an object there to hold the data tiles, and we're just going to use them later. I then have to write these 2 functions. The first one is literally just to add a div to that control area. And the second function is going to look at if I have 3 data layers, it will create 3 checkboxes in that control area. That's all this is doing. Maybe if I was better at JavaScript, this would be easier, but this works. So then I say which layers I want to have in my map, and I go ahead and create the checkboxes. That's literally these functions are calling this earlier functions, so you can create the checkboxes in the control area of the map. Pure leaflet would be easier, but it's not here. I then have to write code that listens for each checkbox. And every time one is checked or unchecked, it will go and redraw the map. This is automatic in Leaflet. I couldn't find out how to do it automatically in deck.gl, so I have a little listener. Each checkbox gets its own listener, and each time you click it, it is going to call a function that we'll call this function. This has all the bulk of the work. It has this one layer, which is really consisting of all of my layers, the GeoArrow scatter plot and the GeoArrow polygon, which will be almost identical to the regular deck.gl scatter plot layer and polygon layer, except the way you access the data is with the name of the data .getChildGeometry. This gives you gives deck.gl direct binary access to the Arrow data. This is what gives you so much speed. This, thanks to Kyle Barron for writing this, that deck.gl now can access the binary data in the Arrow file automatically. And that's crazy fast. We create a tooltip. Now, since we have all these layers together, the tooltips can be different for each layer, but they both have to be in a column called tooltip. And layer filter, that's checking the checkboxes. And if the checkbox is checked, it shows that layer. If it's not checked, it doesn't show that layer. We then finally have a function for actually drawing the map. Each time it's called, it will clear all the layers and draw them again, and it will only display the layers that are checked. Don't worry, it's not doing computations each time. It's actually not even drawing each time. It's sort of just repaneling over the map. So it's very, very fast. It's incredibly fast. We then call drawMap, and that creates the map. And it creates something like this. In your browser, this is a fully zoomable, pannable, interactive map. And it can handle about 4 million interactive points. That's 4 million points on a zoomable, pannable map. And you could put in your polygons here. We have, I believe, all of the little blue dot areas are the polygons, and all the purple-ish areas are the points, because it's 4 million points. Well, here it's actually only 300,000, but I've stress tested up to 4 million points. You could easily toggle off the street maps and show the imagery, or you could toggle off the points, and you can see there's lots of little polygons there. And it's all done incredibly fast thanks to Arrow and deck.gl. And you could combine Arquero for filtering the data to be plotted on the map. And each time you filter the data, the map redraws. But that's for another talk. So we stored all the data in Postgres. We made the spatial queries with DuckDB. We extracted the data into Arrow, and then we visualized it with deck.gl. We covered everything we needed to do at scale. So thank you very much.